Okay, welcome back to the next concept under permutation and combination. In the previous concept, we went through the permutation of n distinct objects. So for example, if I have 5 distinct objects, how many different ways can I arrange these 5 different objects? Right, but now this is a little bit more, it's a subset of the previous concept, which is given n distinct objects, how many ways can I arrange R objects, which is a subset of the n distinct objects. So for example, given let's say 5 distinct objects, how many ways can I arrange 3 objects? Right, so let me just give you an example here. Let's say I got 5 different alphabets once again. Right, I got A, B, C, D, E. Then the question is, how many different 3 alphabet permutations where the order matters? So the way that we actually tackle this, right, and once again, there's also a formula for this, but I'm going to show you how we actually derive the formula so it makes sense to you. The constraint of the question is that we have 3 different slots, right, because we want to form a 3 alphabet permutation. Now in the first slot over here, how many different alphabets can I choose from? In the first slot, I will have 5 different alphabets that I could choose from. Now when we move on to the next slot, how many different alphabets can I choose from? That would be your 4, right? Because after the first one, you will have chosen another one, right? And then now in your second slot over here, you will basically have 4 different options. Now when you move on to the last slot, you will only have 3 options because the first 2 has already been exhausted. So in total, you will have 5 times 4 times 3. So total number of ways, right, will be just 5 times 4 times 3. Now, of course, we will not times 2 times 1 anymore, right? We won't include this because we stop at number 3, right? But of course, if we go all the way, then there'll be times 2 times 1, right? But we are not interested in that because we have 5 different alphabets, right? 5 alphabets, but we only want 3. So we will stop at the 3rd alphabet. So how does this actually link to what we already know so far, right? Remember in your previous question, right, in your previous concept, so the permutation of n distinct objects, right, this is from what you learned previously, is basically just n factorial. But now we are also doing n factorial, but we cut it prematurely, right? We don't go all the way until the end. So this 5 times 4 times 3 can also be visualized as 5 times 4 times 3 times 2 times 1 divide by 2 times 1, right? Because we actually cut away the 2 times 1 away from the 5 times 4 times 3. So if we want to reuse this concept that we learned so far, right, n factorial, how do we actually link it to this scenario whereby we have n distinct objects? And okay, I'm just going to put a note over here. This scenario 1 is that there is no replacement. Okay, I must put here, no replacement. We must put a caveat over here. There's no replacement over here. Now let me just bring this whole thing down here first. Right, there's no replacement. So how do we link it? It's essentially n factorial, which is, you can think of it as your 5 factorial, but then you want to divide away your 2 times 1, right? So if you want to divide away your 2 factorial, which is your 2 times 1, how do you get 2 factorial? You basically take 5 minus 3, right? Because 2 factorial is, 2 factorial is basically just 5 minus 3 factorial, right? Because 5 minus 3 is your 2 factorial. And realize that 5 over here is basically your n, and your 3 over here is your r. Because remember earlier on, we have r objects from n distinct objects. So if we choose 3 objects from 5 distinct objects, your r is 3 and your n is 5. So in other words, your formula over here would just be n minus r factorial, because you're taking 5 minus 3, which is your n minus r factorial. So this is your formula for the total number of permutations without replacement. So I'm just going to write it at the top over here, just to summarize it for the first case, right? So the first case scenario over here, okay, so number 1 is that there is no replacement. The formula would be n factorial over n minus r factorial, just like that, right? But then you have your second scenario, right? And what is your second scenario? Your second scenario will be, of course, with replacement. So scenario 2 will be with replacement. So again, let's just revisit this, use the same scenario again, right? I have n distinct objects, and these n distinct objects will be my 5 alphabets, right? Now I want to choose r distinct objects. So let's say I want to choose 3 alphabets only. So once again, I got 3 slots, 1, 2, 3. I have slot 1, slot 2, slot 3. So if I want to choose 5 different alphabets, and given that I can replace them, that means in my first slot over here, I have 5 different options that I can choose from. But since there is replacement, which means that in my second slot, the alphabet that I chose in my first slot, I put it back into the pool, right? Which means that I could once again technically re-choose that as an option again. So that means that in the second slot, there is a possibility of yet another 5 different alphabets being chosen, right? Because the alphabet that I chose initially could appear one more time, in addition to the rest that did not appear in the first one, right? And the same logic applies for the last one, because it doesn't matter what I choose in the first two, since I replace them into the pool, it could appear again. So that means for this case over here, it's 5 times 5 times 5, which is your 5 to the power of 3, right? So what's the formula over here? You realize that the 5 over here is your n distinct objects, right? And the power 3 over here is your r distinct objects. So the formula for this would just be n to the power of r. So with replacement, okay, I'm just going to write here, with replacement is just n to the power of r, because you pick n objects r number of times, because there is replacement in this context. Okay, so when it comes to formulas, it's very easy to remember a bunch of alphabets, but it's more important to understand the concept, because sometimes when you do the question, that's what we're going to tackle later on after this video, sometimes the concept may not be so obvious to you what it is, right? Which formula, it might not be so obvious, but as long as you understand the concept, it'll make sense. Okay, so once again, as usual, make sure to pause this video to go and try the questions. And once you're done, unpause it, because right now we are going to tackle this question over here. So I have 10 pieces of jewelry, and they are all distinct, right? Different means distinct. So immediately I know I have 10 distinct objects. Now I need to choose 3 to give 1 piece to my 3 daughters. So 10 distinct objects, choose 3 distinct. Right? So this is very familiar because it's what we did just now. Right? You had 10 distinct objects, now you need to choose 3. So how many ways can he do this? So once again, I got 3 slots. You can imagine 3 slots, right? This is daughter 1, daughter 2, daughter 3. Now for the first daughter, right, how many different pieces of jewelry could I give her? Right? I could give her 10 different pieces. Why? Because I have not given anyone yet. But after I've given the first daughter, right, that would mean that my next daughter would only have 9. And sometimes in the question, it's not so obvious, like they won't explicitly tell you whether there's replacement or not. But in this context of the question, right, you have to exercise some common sense, like really some common sense, to figure out whether there's replacement or not. And in this case, if we give one of the daughters a jewelry, then obviously we won't take it back from her, right, to give the next one, because the next one must get a distinct one, right? And the 2 daughters cannot have the same piece of jewelry. So this is your classic case of without replacement. Okay, so this without replacement portion needs to come as a common set. So this is without replacement. And then the last daughter would have 8 different pieces of jewelry that she could receive, right? So the total number of ways would just be 10 times 9 times 8, which will give me 720 ways, right? But more importantly is, how do we actually use the formula that I taught you previously? So recall that 10 times 9 times 8 is basically your 10 times 9 times 8 times 7 times 6 times 5 all the way until times 1 divided by 7 times 6 times 5 times all the way until 1. Right? We actually divide away the rest of the factorial. Right? So this, in other words, is your 10 factorial over 7 factorial. Right? But, in the context of this question, we don't know, like, it wouldn't come naturally to us to put 7 inside. So how do we actually derive the 7? The 7 actually comes from the 10 factorial divided by 10 minus 3 factorial, right? Which is also your formula that you learned previously, which is your n factorial over n minus r factorial over here, right? So if you identify this case in the exams, immediately you can use the formula as such. Otherwise, you can just use common sense to figure out the answer as well. Okay, so yep, that's it for this question. Let's try the next one. And this is the next question. So once again, feel free to pause this over here before we actually tackle the question together. If not, I'm going to be assuming that you're done with it already, and let's just jump right into this question over here. So again, we have 4 cars, and I'm just going to write car 1, car 2, car 3, car 4. Right? And each car is to be painted in one of the 3 colors, red, blue, or green. How many ways can this be done? So you realize that for, let's say, car 1, right, I could paint car 1 in red, blue, or green. So how many options are there for car 1 to be painted in? Right, I have 3 different options. Now for car 2, if car 1 is painted in a color, does that mean car 2 cannot be painted in that color? The answer is no, right? Car 2 could be painted in the same color as well. And therefore, for car 2, there is 3 different options as well. Right? And then for car 3, there's another 3 options. And then for car 4, there's also another 3 options, right? All of them can be the same color, right? There's no restriction of that. So all in all, how many different ways can this be done? So the total number of ways to paint all the 4 cars would be 3 times 3 times 3 times 3, right? Car 1 got 3 branches, and then from there you form another 3 branches, then you form another 3 branches, and then form your last 3 branches. So you can imagine, right? Your first 3 branches, this is car 1, and from here you split out another 3. This is your car 2, and then from here you split out another 3 again, and you just carry on all the way until car 4, right? And then at the end, you will have 81 different ways. But using the formula that we learned earlier, right? This is essentially your 3 to the power of 4, which is your n choose r. Why? Because you have your 3 different options. So, right, n is 3. And how many times do you choose it? You choose it 4 times, which is your r, right? Because this happens 4 times over here. So this is your classic case of n choose r, which is your r distinct objects from your n objects with replacement. Okay, so sometimes the formula may not be too obvious to you, but I promise you, it's definitely, there's a formula there. But if you're not able to identify which formula to use, it's perfectly fine to derive the answer using common sense like this as well. Okay, if not, that's it for this over here. Let me know if you've got any questions in the comments. And with that said, I will see you in the next video for the next concept.